Right, so we're going to talk a little bit more about maxima and minima, right? Just extrema. So take a look at this. Take a look at this graph over here, right? So you see how, we've got places where we have maxima and minima, right? Like, for example, take a look at this place. This is where the derivative is 0. It's a critical point, and there is a maximum here, okay? Now, take a look at here. The derivative is also 0. That's a critical point as well, just like this, but there is no maximum or minimum here, right? So what's the difference? If these are both at critical points, what in addition then is giving us the maximum and the minimum, right? So what do you guys think?
It's differentiable, maybe continuous.
They're both differentiable, but why is there a maximum there and nothing here?
It's the highest point.
Right? So basically, exactly. So basically what's happening? The derivative here is positive. The slope is positive. It's increasing. And then it switches between increasing and decreasing. That's what gives you a maximum there. But here, it's increasing, and then it continues to increase. There is no change in increase, decrease. That's why, even though it's a critical point, you don't get an extreme value there. All right? So, to get a minimum or a maximum, not only do you have to have a critical point, but in addition to that, you have to have a change from increase to decrease. So look here, f prime is undefined right here. So that's also a critical point. But then how do you also get a maximum? Because it changes from increasing to decreasing. Okay, so that takes us to what we call the first derivative test. The first derivative says, at any critical point, if f prime changes sign from positive to negative, then there is a local maximum. So look here. There is a critical point here. F prime is positive here. The graph is increasing. F prime is negative here. The graph is decreasing. When it changes from positive to negative, increase, decrease, you get a maximum. And then, if f prime changes the opposite way, from negative to positive, then there is a local minimum. So look here. This is a critical point. F prime changes from negative to positive, so now it's a minimum. Okay? All right. Huh? Right, correct. It's like a relative. Okay. So here, like what we said before, even if there is a critical point, if there is no sign change, then there is no local extrema. Okay? All right. So what happens at an end point? So suppose you're at an end point. If to the right of the end point, the graph is decreasing, then this is a local maximum, right? Because it's decreasing from a higher level up, okay? If at an end point, after that, the graph is increasing, then this is a minimum because this is the low point from which the graph is increasing, okay? So these are just endpoints. The other way, if you have an endpoint, okay, and now we're on the opposite side, on this side of the endpoint. If the graph is decreasing to the endpoint, then this is a minimum because it's a lower point. But then if it's increasing to that point, then this is a local maximum. Okay? So do you see how, does it make sense to you, intuitively, right?
Yeah, we need this.
Huh?
Can you say this part?
This part? Here you have an endpoint. That's like a wall there. The graph ends there. But do you see how the graph is decreasing to this point? So this is the lowest it's going to the endpoint. That means this is a minimum because the graph is decreasing to there. And then here the graph is increasing to this point, so this becomes a local maximum. Okay, right. So let's use...
Sorry. Anytime there's a change, it's either a min or a max?
if there is a change in the slope at a critical point, you get a min and a max. Okay, so yeah, let's use the first derivative test to find local extreme values, right? Local extreme values is not talking about absolute minimum or maximum. So, we're going to do the number line here. So, let's figure out the domain. What's the domain of this? Good. Okay, so to do this, same story. We take the derivative. And then we set the derivative equal to 0. And then we factor. Let's factor out a 3 first. So this is 3, x minus 2, x plus 2. So x is 2, x is negative 2. These are points where the derivative is 0, so they are what type of points? Correct. Okay, so we're going to put this on the number line. This is the domain, and remember this is f prime. So, negative 2, positive 2. Now, let's pick a point from the leftmost region. We're going to plug it into here. The parentheses is where I like to plug them in. So if I plug in like negative 10, I get negative, negative, positive. What if you plug in 0? What do you get? And 2? Or like greater than 2, positive. Okay, so this means the graph is increasing, decreasing, increasing. So now, here's a critical point. At the critical point, the derivative is changing sign from positive to negative, so you know there is a maximum there, okay?
This is kind of the same thing with the mirror.
Exactly.
So what do we find out that's different?
Once we figure out the slope,
Exactly. Once you figure out the slope, then you don't even have to draw this, basically. Like, you just know. And then eventually, right, you can have word problem types, and they say if the derivative is positive here and it's negative there, what do we know? And then you know that there's a minimum or a maximum.
Okay, isn't that what we did before?
Yes, but now it's basically more technical language.
Okay, but it's the same thing.
It's the same thing.
Okay.
So f of negative 2, where do we plug it in? The original function, and we get 11. And then there is a minimum, f of 2, negative 21.
So this is the answer?
Yep. Okay, now take a look at this one. Now, we have to take a derivative, but what are we going to do to take a derivative here? Product rule. Okay, so u will be x squared minus 3, v e to the x, u prime 2x, v prime e to the x. So f prime of x. So I didn't do the domain for this because look, they already gave us a domain. Okay? So this is going to be this. I'm going to write the e to the x first. So it's e to the x squared minus 3. Remember the parentheses. And then plus 2x e to the x. It's so hot in here today. I don't know what's going on.
So stuffy.
Okay. So look. Okay, so look. You see how there are two terms here? You see?
sorry, I didn't.
You see how there are two terms here? Right? Both of these terms have a common e to the x. So what I'm going to do is factor out an e to the x.
Oh.
So I get x squared minus 3 plus 2x. And now let's write this in better form. Standard form like this. Factor it. Look at you guys. So now, okay, so look, calculus kind of paused here. This was like algebra-ish stuff. And now we're going to set it equal to 0.
Wait, what happened to x to the x?
Factor out the x.
Oh.
So now, okay, e to the x is never 0. Okay?
Took 1, right?
You can, e to the x is never 0. So here, this gives you x equals -3, x equals 1. So e to the x is never 0.
So we just ignore it.
Yeah. So these are the critical points. Okay.
Just something you know that e to the x is never 0?
Yes, from Algebra 2 and Pre-Calc, e to the x has a... Okay, think about it. Can you plug in a value for x and make e to the x 0? No.
Well, I could. You ignore
Okay.
it because it's never 0?
Yep. So now we're going to plug this in. This has a set domain. Okay? -3 and 1. Okay. Shh. Yep.
Why don't I understand why you didn't take out like x e to the x? Do that on both sides.
I did take out e to the x from
No,
here.
x e to the x, like x plus x.
But there is no x in this term to take out. Like you just have e to the x
You
and an
can't
x.
take that one out.
No. Yep. Okay. So now, guys.
Does it probably have like a calculator?
Huh?
Does it have like a calculator?
Not necessarily.
Okay, so we should just know how to like -4.
Okay, but listen. Here's how it's going to work. All you care about is if it's positive or negative. So take a look. From here, let's say we do take -4, right? I'm going to plug it into this. Okay? Look, even if I had e to the -4, that doesn't make it positive or negative. It doesn't change positive or negative, right? It's still positive. And then here, -4 in this parenthesis will give me negative, so that's positive.
Wait, e to a negative exponent is positive?
Yes, because if you had e to the -2, it's just 1 over e squared.
So
Okay.
E's like always going to be positive.
Right, unless there's like physically a negative outside. Okay, if I plug in a 0 here, then it's negative. And if I plug in like a 3, or yes, a 3, then it's positive.
Yeah.
Okay, so now, we know, okay guys, come on. We know there is a maximum here and a minimum here. Okay? But now, look, remember what we just learned about endpoints here. If there is an endpoint and something is increasing from there, then there is a minimum that's produced there. Okay? And then here, there is an endpoint, and the graph is increasing towards there, so there is a maximum produced there.
Those are the absolute.
No, not necessarily. We don't know until you try. So now you're going to plug everything. So where are the minima? You have a minimum at f of -5, f of 1. You have a maximum at f of -3, f of 5. Okay, so let's see what we're going to do now. Okay. If you don't mind, I'm going to start from the very bottom, okay? Because it's a positive number. 5, we're going to plug it into here. So what are we going to get? 5 squared is 25. Minus 3 is 22. E to the 5. Let's leave it that way. Okay? Now, let's do the 1 here. The f of 1, because it's positive again. 1 minus 3 is -2. E to the 1, which is just -2e. Okay? Now, let's do this very first one. Okay? -5, you plug it in here, what do you get? 25 minus 3? 22. E to the
5.
-5. Which is what? 22 over e to the 5. The last one, you plug it in. 9 minus 3, 6. e to the negative 3, 6 over e cubed. Okay? And we're not looking for absolute min or max here. It's just one of the local min or max, so that's it. Okay? So do you see how it's very possible? Yeah. Okay. All right. All right. So let's talk about concavity. Okay. Concavity talks about if the function is concave up or concave down. All right? So what does that mean? Basically, concave up, right? So if you have like a container or whatever, right? You see how like this is like kind of right side up, and then this is kind of upside down? That's what concavity is, right? So if you take a look at this one, how it's right side up, if you split it, this or this, you see how they kind of like cave up? We call this concave up, okay?
Leave the door open a little, maybe.
Sure. Can you, Mila, can you maybe open the door? Okay, so these are both concave up. But then if you have this, these are concave down. Okay? Yep, yeah? Yep, okay. The way this happens is when you have the slope, and if the slope is getting more and more steep, it creates concave up. If it's getting less and less steep, it creates concave down. Okay?
Less steep.
Yep, exactly. That's exactly what it is.
It's still steep.
Yeah, but it's like the change. So don't worry about that one too much.
But it's concave down.
What about the spiral thing?
Yeah.
Oscillation.
Okay. Okay, what are we talking about?
No, it has nothing to do with it.
It's the band.
You know, it's fun. It's somewhere here in the
It's okay.
It's fun. You got this.
She fixed it.
Oh my god.
Our hero.
Okay. It's okay.
It's the base. Yeah, it's just the back.
No.
It's
Okay,
definitely has a feel on my feet.
we'll just talk about this. It's fine. So, how do we figure out concavity? Until now we've been dealing with first derivative. Take the derivative, do the sign chart, positive, negative, blah, blah, blah. Same exact deal, but now we're going to look at the second derivative. So if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. So that's all right here. Okay? All right.
Second derivative is negative and it's concave down.
Okay. So look. Let's do this example, and you know how to do this, okay?
Wait, why second derivative?
Okay, go with this. Okay. Let me do the problem.
Just do it.
Okay. Use the concavity test, which means second derivative. Basically, what we're figuring out is where the graph is concave up or concave down. All right, so here's what we're going to do. First derivative, we know how to do this. Okay? That's not for concavity. Now we take a derivative again. Okay? Now
Yeah.
so this is 24x. Wait, what did I just do?
You erased it off.
No, yeah, so.
No,
plus
hang on.
24x.
Yeah.
You did it right.
Oh, yeah, okay.
Just that.
Okay, so now we're going to set this equal to 0. So let's factor out a negative 12x, and then we get x minus 12, and we're going to set it equal to 0. I'm sorry, x minus 2. Oh my. So x is equal to 0, x is equal to 2. But now this was for the second derivative, right? So we go over here, same idea, but this time it's y double prime. Put in the 0, put in the 2. Okay? Now it's second derivative, so I'm going to plug my numbers into here. So,
Are those 2 points, are those critical points?
no,
They're not critical.
no, this is second derivative.
Okay.
Okay, so now,
What are those?
okay, hang on. Okay, they're nothing. So far they're nothing. They're just points where the second derivative is 0. Okay, so now, plug in something from this region into here, and you get negative. And then, like, if we plug in a 1, we get positive, or if we plug in like a 10, we get negative. Okay, so now we did the same exact thing, but now it's for y double prime. Whenever it's negative, we say it's concave down, concave up, concave down. Now, take a look. Now let's go to the points here. You know, maybe I'll come back to that later, okay? So, it says determine the intervals on which the graph of the function is concave up or down. So basically, where is it going to be concave up? So it's concave up from 0 to 2, and then concave down, negative infinity to 0. Okay?
And is it always with the open
Yeah.
parentheses?
Okay, now, let's talk about those points. At this point, do you see how the concavity changed from concave down to up? Whenever the concavity changes, then that point is called a point of inflection. Okay? So, for it to be a point of inflection, it's not enough to just qualify to go onto this number line. It goes on the number line from here, and then in addition, you got to do the signs, and only if the signs change is it a point of inflection. All right? So both of these right now are points of inflection. We're going to come back to this over and over again. Okay? If it's asked first. So here we go. Point of inflection is the next thing we're talking about. So a point of inflection, I have like a whole order of, that I go with here. So a point of inflection is a point where basically the concavity changes. That's what you have to figure out. So y double prime changes from positive to negative and vice versa. Okay, so let's do this one. All right, find all points of inflection of the function. So y prime is 12x squared minus 4x cubed, but that's not what I want. I want y double prime. 24x minus 12x squared. Okay. Okay. What can I do here? Factor out what? And I get 2 minus what? Just x. Oh my, okay. So set it equal to 0. X is 0. X is 2. Okay, go on the number line. Was this the same problem that we just did? Yeah. Oh my God. No wonder. Okay. So,
Would x be negative 2 then?
so we say, here, huh?
Wouldn't x be negative 2 in this one?
No.
No, because 2 minus x is 0, and then, so 2 minus x is 0, and then add x to both sides. So 2 equals x.
Oh, okay, so it's the exact same.
Yeah. Yeah, so, okay, so then we say point of inflection, it's POI, x equals 0, x equals 2, but then plug it into the y, so you get that it's 0, 0, and 2, 16. Okay?
plug it into the original y?
Yep.
Or y?
Original y.
So you want it as the points, that's the right way to.
You plug 0 into this, into the y. You plug 0.
Oh,
Into
into there,
here.
2 into there. and then
Yep.
Whatever you get.
Yep. Okay, let's do another one. Okay, this one is the, this. Yeah. I also got distracted with all that. So now I'm back. Okay? All right. So, product rule. Okay? So u prime is e to the x. V prime is 2x. All right? So y prime is 2x e to the x plus x squared e to the x. Now you have to find the derivative of this. Now you have to do it again. Okay? But you can factor out an e to the x.
Can you just do product rule then?
It's too much because then you end up doing two product rules.
You can't take an x out of this one either. There's no parentheses.
Okay, yes you can. Okay, hang on, look. Okay, take a look. If you take out an x as well, then you get x e to the x times something else. And that's 3 terms being multiplied, and you can't do product rule like that. So the thing is, I wanted to minimize product rule, so I only took out e to the x. So you should train yourself to just factor out e to the x. E to the x is always very common to just factor out on its own. Okay? Like for all of math eternity. So now we can do product rule. So u is e to the x, v is this. I always feel like I'm doing grammatically, I'm being grammatically wrong when I say u is. Okay.
Isn't it just 2 plus x?
Huh?
Isn't it just 2 plus x? Does it stay 2x for each?
V or E?
I don't know. Okay. Okay, hang on. Let me focus here. Okay. All right. Okay, so u prime is e to the x, and v prime is 2 plus 2x. Okay? So what's y double prime then? It's going to be e to the x times this, right? So
So it's e to the x times 2 plus 2x.
plus e to the x.
Times 2x plus x.
Okay, so now do you see how we're going to factor out the e to the x again?
Yeah.
Okay, so e to the x, and then we get 2 plus 2x plus 2x plus x squared. Okay? So this is e to the x, and then what's this? X squared plus 4x plus 2. Okay, so now when we set that equal to 0, what would the next step be? Factor, right? Okay, so, but the problem is this can't be factored. So what then?
Quadratic formula.
Yeah. Okay, so this can never be 0. So x is negative b plus or minus the square root b squared minus 4ac all over 2a. What's 16 minus 8? 8 over 2. So negative 4 plus or minus 2 root 2 over 2 negative 2. Okay, so now when you're here, you can divide everything by a 2. Plus or minus root 2. Okay? All right, so that's the quadratic formula. Now we're in calculus. We're not going to relearn this. Okay, so now look. Now these have to go over here somehow, and there's no way we know how to get them anywhere, right? But now we've been showing all the work, right? And presumably for this problem, it would be a calculator section, but you've shown all the work. So you can plug that into your calculator. And you know what? You don't even have to, because look, this is one of them and this is the other one. Okay? So you can plug it in your calculator and you get like the decimal value, but basically these are it. So why double prime? So now from here, if I plug in 0 here, I get positive, right?
Wait, why are you plugging into y double?
Because this is y double prime.
Oh, so you wrote y prime.
Oh, that's y double prime, yeah. Okay, so now, like something from the leftmost region, like -10 or something, it's going to be, I feel like I made a mistake somewhere.
Couldn't you?
You know what? I am going to, I tried to say it'll be like easier. Okay, so 0 works for above, so it should be positive here. And then it's also positive here and negative here. Okay? So where are the points of inflection? Right.
Is it always looks like it's the same?
No. It's what's on here and if the sign changes around it. So if you had positive, positive, negative, right? Suppose, okay, so I'm going to change this, but like suppose it was positive, positive, negative, right? This would not be a point of inflection. All right? Okay. So lastly, I'm going to skip that for now. So lastly, I want to do this one. So it says use this graph to estimate where f prime and f double prime are 0, positive, and negative. Okay? So let's do this. So where is f prime 0? How do you figure out if f, what does it mean f prime is 0? The slope is 0.
And something.
But what does it mean f prime is 0? The slope is 0, so what does it look like on this graph?
Tangent
Where
line.
would it's a horizontal,
Yeah.
it's a horizontal tangent. So the slope is 0 here and here. Okay? So this is where the slope is 0. All right, so f prime is 0 at x equals -1/2, x equals +1/2. Okay, so now we want, where is f prime positive? F prime is the slope. Where is the slope positive? This means where it's doing what? Increasing. So that's from -∞ to -1/2, half to infinity. And then where is f prime negative? Decreasing. -1/2 to 1/2. Okay, now we want to talk about f double prime. Where is f double prime positive and where is f double prime negative? F double prime positive means concave up. So where is this concave up? Okay, so do you see how we always read left to right, right? Do you see how this is always like concave down here? And then it switches to concave up? Okay, so math is symmetric. That switch happens smack in the middle. So right about here, it happens halfway. So from 0, from x equals 0 and on, it's concave up. So 0 to infinity. And then it's concave up from -∞ to 0. And then where is f double prime of x 0? This is where the concavity changed. So that's at x equals 0. right? So that's also like the point of inflection. Yep.
Wait, so the top one's concave up? You're concave up above like the is greater than 0. Is that
Yes. But it's this one's like 0 to infinity here. It's concave up here because it's like the upper, like it's facing up like the bowl.
oh yeah.
Yep. Okay, now, next one. So take a look. This is where like calculus is really getting like calculus E, right? Because you have to now really read the instructions. So it says use the graph of f prime. So now this graph is f prime, not f. Okay? And then to estimate where f is increasing or decreasing. So, okay, so how does that work? So let's see the relationship. Whenever f prime is positive, what's f doing? Increasing. When it's negative, f is decreasing, right? Okay, so now this graph is f prime. Whenever you see a graph, how do you know where the graph is positive?
Increasing.
Not increasing, that's increasing, but how do you know it's positive?
Right or left?
Oh, x-axis.
Up or down?
Oh, up or down.
Okay, so anytime any graph is above the x-axis, it's positive. Anytime it's below the x-axis, it's negative. A graph being positive or negative is the y values being positive or negative. All right? So this whole region here, the y values are positive, so the graph is positive this whole time. But then this whole time here, when it's below, the y values are negative, so the function is negative. So the graph is negative. So over here, f prime is positive. And over here, f prime is positive. So what's f doing in those red regions? Increasing. Okay, so f is increasing from negative infinity to negative 3. Because f prime is positive.
But, okay.
It's going
If
down.
f going, exactly, f prime is the slope.
Right,
So
f
it's
prime
like-
is the slope. This is f prime. This
Yeah,
isn't f.
I know, but you just said f prime is positive,
Right.
but if it's going
Right.
downwards, it's negative.
Okay, but you're looking at f. This isn't f. F would have been going down. That would have been a different thing. This is f. This is just the slope. This is
So if
f
I take
prime.
like the actual number values of x and y when I'm making
Right.
the slope,
But it's only when this is the graph of f prime.
okay, whatever. I'll
So where is f negative? So f is decreasing negative 3 to 3. Okay? So the thing is, until now, whenever we're given a graph, it was f. But now we're finally given a graph of f prime. So it looks different.
Makes sense.
Oh, it's negative.
Are the notes? Is it just screencast?
Yeah, but I post them online.
Okay, okay.